problem. So why we need to intervene the multi-agent system? In many practical situations, we need to guide the system to the desired behavior. So the behavior, the dynamical behavior of the multi-agent system may not be the one we need. So the behavior resulting from self-organization may not be the one we expect. And what we can do to control the collective behavior without changing the local role of the system. That's a problem is different from the traditional control problem. Because you say without changing the local roles of the existing agent. Okay, we call this as a soft control. Let's illustrate this idea using a very simple case. So the system may have many agents. Each agent follows a local role and autonomous distributed. Agents interact locally with each other, and the control to change the local roles with existing agents is not allowed here. And the idea is add one or more, or remove one. A special agent we call the shell is controlled by us, but not following the local role. And the shell is treated as an ordinary agent by the existing agents. And the ordinary agents may not avail of the control, so we call it soft. Here is a case study. We have a system, a group of n agents, initial condition like this. Our goal is to control the agents to move in this direction. And the soft control design a shell based on the agent state information. So that's a definition, that's a design of the one. So you can show that with this one, you can control, will lead to synchronization of the group. Without changing the existing local interaction role of the agent. That's a key point. Here we have a demonstration. So the shell moves from time to time and guide the group of agents to some direction. And so you can see almost synchronized. And the local roles, interaction roles, is not changed. And the same, keeps the same. You can also do something more, and to avoid jumping. So here is you can do things like this also. Okay. I would like to mention that it's not just for the Bao model, maybe applied to other multi-agent systems. And add a special agent is just one way. There should be other ways for different systems. For example, remove some agents, put some obstacles. So that also can be regarded as the soft control method. So finally, let us consider another intervention method called the leader-follower model. So I think many of our colleagues here are familiar with this one. And let's have a look. So we have a group of agents, some ordinary agents, some we call it a leader agent. So slightly different from the previous one, because the previous one, soft control, use feedback. Here, there is no feedback at all. So add some very few information agents called leader to intervene in the existing agents, treated them as ordinary agents. So what we can control is a proportion of the leaders. Proportion means the number of leaders divided by the population size. As I mentioned before, this is an open loop intervention and easier to manipulate. Okay, let us have a look of picture. So in some biological system, a small number of agents have pertinent information about the destination. They can help to induce the whole group. Here is it's a paper published in Nature. The simulation result shows when the population of leaders is small, the leaders cannot induce the agents to the expected direction. However, when you increase the proportion of the leaders, I mean, things will be different. However, you will see that the larger the population size, the smaller the proportion of leaders is needed to guide the system. Here is a real experiment, shows that so on a vast oceanic fish shores show that the small set of leaders significantly influence the actions of a much larger group. Let's have a look at such questions. How many leaders are really needed for the expected behavior? So to answer this question, we focus on the intervention of the bound mentioned, the Floki model, and we provide a lower bound to the ratio of the leaders and the followers. Okay. Here is a serum intervention with decreasing ratio. As I said before, with the increase of the population, the ratio of the leaders can be decreased. This theorem says for any parameter V and R, if the proportion of the leader, number of leaders divided by population size, satisfies this lower bound, you can really see the lower bound can decrease to 0, okay, as n tends to infinity. So when n is the size of the population, then all the agents will move with the same expected direction eventually. So this really gives a lower bound how many leaders are really needed. You can have something more maybe, and an impossibility theorem. Suppose that the initial angle is not 0. If the proportion of the leaders satisfy this one, I mean, if Rn is larger than this one, and that's a radius, that's a speed, that's a proportion of the leaders, then the leaders cannot guide the followers to the expected direction almost surely when the population size is large enough. So finally, there are, I think that's already 50 minutes.